Sorry.
Dang, so many technical errors in one day.
1 second, I can't hear you. Hang on. I gotta switch some stuff around. And okay, now I can hear you. Sorry. Yeah. Oh my God. Okay, it's just not my morning. In terms of technology, at least, that kind of kills me. Okay, let me get my stuff back up, and then we can continue. Here we go. Share screen, and oh, we're back. We're back. Okay. Good. Okay, excellent. Well, yeah, so this is, okay, we were way lower than this, right? Okay, now back onto more stuff that, we've seen and talked about, right? So configuration is probably going to be a substantial portion of this, or at least if my predictions wind up being right, which, well, who knows, maybe I'll be lucky for once and get it right. This seems like the sort of thing that they could ask a lot about, and I know it's been a large focus of the class, right? The professors have emphasized that the kind of theme of the exam will be like the big picture topics more than like the real fine details. That being said, molecular configurations are kind of a big one, right? So, I mean, resonance being one of those too. I'm not too sure how they'll ask a ton about resonance on the final, but your guess is about as good as mine in this case, right? And they like to be creative, so they very well could ask stuff about it, and it is like a really big and important topic, right? But then Newman projection and stuff about like rings, that seems like the sort of thing that might be really big. There's plenty you could ask about that in terms of multiple choice, right? It's totally really possible to do it, and you've spent a whole ton of time talking about it. Okay. There's all these definitions. They might just ask like 1 or 2 definition questions, right? That's like on the normal final, that's like a really common thing that they do, is just ask about typical definitions. They normally ask you to like give an example or explain it, but well, I could totally see them trying to retain some amount of like the structure of the usual final and asking stuff like what the definitions mean, or maybe not so much that, but they might ask you like choose out of a list an example of something to show that you know what the definitions do mean, right? Same thing goes for isomers. Yeah, they could really ask about this. One thing to mention, and that I didn't actually include on this list, but I've never ever seen it come up on any exam or final, but like I know it's usually talked about. There's these like quantities like enantiomeric excess or like optical rotation or something. You can calculate these things in some way. I've never seen them come up, but maybe they could, right? They're totally the sort of thing that you could just ask and have somebody type in a number, right? They're not really like, I don't think they're really big picture topics either, but like, I don't know, it's the sort of thing to keep in mind. I personally wouldn't really focus on them, but it's like, again, these are the sort of things that you can never really know, right? And then stereochemistry stuff, they probably won't ask about like differentiating between R and S. I don't know, maybe they will. Again, I can never really tell, but this is the sort of stuff that also like matters and was a big idea. Okay. In terms of reactions, I mean, normally the whole final focuses on primarily reactions, right? But this is a harder thing to really focus on and talk about in a machine graded thing. I mean, I have a hard time imagining that they'll really try to detach from the like conventional reaction side of things, because again, I mean, most of this course has been about reactions. After about a month or so in, this was kind of the theme, right? But there's some fair amount of reaction stuff that you could do in terms of ranking, right? Which of the following like carbonyl group containing compounds will react the best with this certain organometallic? Or like, which of these are the best nucleophiles, or which of these are the best electrophiles, meaning that they'll react the fastest with some certain nucleophile, right? Those are all sort of things that that could totally work in terms of reactions that are, you know, all machine graded, and they really test how well you know what reactions do what. So yeah, this sort of stuff totally can come up, but I don't know, a bunch of other these things won't necessarily be involved, right? Like the differences between these sort of things, like concerted and multi-step reactions, or like hydride and alkyl shift, which is normally a really always, I mean, like always in this course is a really big concept, right? But like this year might not be that important, because what are they going to do? Show you a bunch of potential products, one of them which has an alkyl shift, and then you'll be like, oh, I totally would have forgotten about that, but thankfully they told me the answer because it has an alkyl shift, right? Like I don't know if they would do that. So stuff like this, I don't know if it'll be super important this year, but where other stuff can be, right? An important theme also being like the Hammond postulate that you did see in terms of free radical halogenation. This is the sort of thing that might be important, or they might try to slip in there in some way. It's always a big kind of idea. Okay. You spent a lot of time in this class this year talking about rate reactions. So SN1, SN2, E1, E2. And so these are all kind of big and important key topics, right? So like nucleophile strength, or how good an electrophile is. So that also has to do with like stuff about steric effects, what leaving group you have, well, I mean, you could also talk about what solvent you're doing this stuff in, right? Maybe they'll ask you, like, let's say you want to do this reaction, what are appropriate reagents and reaction conditions, right? And they give you a whole list of potential stuff, right? So knowing this will be kind of important. It's worth mentioning that this list of stuff to review, I'm not telling you the answer here, right? I'm not saying like what the solvent is that you want to use for each type of reaction. That's up to you to go and figure out. I just meant for this to be a list of topics that you should think about and go back and review. Okay, so the hard work is on you guys, but hopefully a lot of this stuff seems familiar at this point, right? Yeah, and so okay, stereochemistry. Obviously, they'll be trying to ask about that in some way, right? Knowing how it propagates is kind of key and important. Yeah, okay, so we learned a whole bunch about halides, right? And like, yeah, okay, we learned stuff about halides with like free radical halogenation, but again, halides, like this sort of stuff comes up again later, right? Just a few weeks ago, you learned how to replace an alcohol with a halide instead. This is like the sort of thing that, I mean, totally comes up all the time. Okay. Oh, somebody had asked earlier, sorry, I didn't have the chat open because, you know, technical issues. What the difference between like vicinal and geminal is. Let's see. So geminal is when two substituents are on the same carbon. Vicinal is when they're on the same carbon on a double bond. Is that right? Someone might. Anyone want to correct me? Okay, no, never mind. So geminal is on the same carbon. Vicinal is just on two adjacent carbons. Yeah, that was it. Yeah, I was thinking double bonds for whatever reason. There's a different word for. I think there might be a different word for. Okay. Oh, you don't. Okay, maybe these terms haven't come up. That's okay. Then you don't need to worry about them. Okay. Yeah, in that case, you probably won't need to worry about them if they haven't shown up. But yeah, this just means on 1-2 carbons, and geminal is just on the same carbon. But if it never came up, then don't worry about it. Yeah. Okay. Okay. Right. And then there's reactions with alcohols, which honestly, when you think about it, made up a substantial portion of like what you've learned like in the class. Right. So you could hydrate or dehydrate, right, to either make or take away an alcohol. You could tosylate an alcohol, which is, you know, to make it a really useful thing. Okay. Like just above, you could replace it with a halide. That's fine too. You can make them with oxymercuration and reduction. This is a great way to make ethers as well, which is always something that's really easy to forget about, but it's super, super useful as a reaction, right? And then you could use this to make ketones too. And that involves a keto-enol tautomerization, right? Which is not going anywhere. You will see it again next semester, and you very well might see it on the exam in some way. Not sure how, but you'll definitely need to remember and keep it in mind. Okay, right, and hydroboration oxidation, you can use it to make aldehydes and ketones as well as alcohols, right? Again, if you put it on an alkyne. Okay, lots of alkene reactions. You've seen these, right? Adding halogens, making an epoxide, which will get you inevitably an alcohol, right? You could dihydroxylate. You can add an H and an X, right? Where an X is like a halogen, so there's free radical halogenation, the standard, like the typical addition, right? The difference between anti-Markovnikov and Markovnikov here are pretty essential, so always important, right? And then ozonolysis and potassium permanganate, that's normal. Okay, cool. Right. Oh, this should be hot concentrated. I'll fix that. Okay. Stuff with alkynes, you learned a few reactions with alkynes that the adding hydrogens or generally doing reductions on them are kind of like the big ones that you learned, right? But you could use them as nucleophiles too and do some cool reactions. That's also a thing. Okay. Recently, you learned all these oxidation reactions, right? We just talked about those like a week or two ago. Yeah, knowing this stuff, maybe I'll get rid of this stuff because knowing the mechanism probably won't be so important because they can't ask you to write out the mechanism. They might ask some questions that involve knowing the mechanism, but they won't ask you to write it because, well, machine graded, right? Stuff about reduction. Okay, knowing the difference between lithium aluminum hydride and then sodium borohydride is pretty useful and important, right? Also remembering that adding these hydrogens using these different methods to a multiple bond is also pretty good and important. That's also a reduction, right? As I've emphasized, the differences between cuprates and organolithiums or Grignard reagents are pretty key and essential. We've talked about it a few times, like last week or so. So I might refer you to see what we wrote and talked about last workshop, or like a workshop or two ago in like the notes. But this is like the sort of thing that totally translates into like a multiple choice question or something. So there's a whole lot to say about this whole topic, right? Okay, and then there's some named reactions, right? And then there's a section on spectroscopy. Fortunately, I don't think you have to know it unless anybody knows otherwise. In usual years, spectroscopy makes up 30 out of 100 points on the final, which is really nasty. But fortunately, you guys don't need to learn it, right? Or at least I don't think you guys need to know it for the final, unless they've said otherwise. Anybody know if they have? No, it doesn't seem like it. Okay, all right. In that case, then you probably won't need to know it. Okay. You can save it for Orgo Lab. All right. Well, in that case, why don't we actually do some problems, right? Because that's what you'll be doing for the final. So, you know, probably useful to actually work on some of those. Okay. So why don't I, I already had the document prepared with like a bunch of problems on there, but now I got to put that back up. My computer really did me over. Okay. That's fine. Oh no, just kidding. Oh, nice. It recovered the file. Okay, so I have the problems up already. Why don't I share those, and why don't we get going on those, right? And then I know, like, I think like last workshop, maybe the one before, I put up the problems and then kind of said like, okay, well, have a minute to work on them, and then we'll talk about them after, right? So we'll do a similar thing too, right? So I have a couple polls set up so we can use those, right? I'll give you guys a few minutes to solve these problems, and then we'll talk about them briefly afterwards, okay? Here we go. So let me share these, right? And so these first are not well, they're not ranking problems, but they're going to be just like kind of multiple choice, pick the best ones. Okay. So this is what we're working with for right now. Here we go. Okay. So these are our 4 problems. I'll leave my screen up, and while we're at it, let me press that button. And so here you go. There's a spot for you to write and send your answers. Okay. Obviously, A corresponding to the leftmost one, B they're not lettered here, but like you get the point. Okay. Why don't I give you, I don't know, a few minutes to work on them. Once you have them down, fill out some answers, and I'll see them trickling in, and then we'll get started. All right, we're back. Okay. Hopefully that was good. If you didn't get the answer, well, keep thinking about them. Well, let me use that. Okay, so here's what we're working with. So over here, okay, for the most acidic phenol, most of you went with the last one, C. Okay. And those of you that did are right. Yeah. So C winds up being the most acidic phenol. Let me make this small. Here we go. Okay. Yeah. So this is the most acidic one. Anybody want to tell me why, in a single word, why this is the most acidic phenol?
Resonance.
Yeah, exactly. Right. So let's say for A, yeah, in a single word, this is the most acidic because of resonance, right? Specifically, we look at the conjugate base. That's such an ugly structure. Right. Okay, and we can fill in and actually draw the bonds, right? Drop this down, move this guy over here, right? But that's not that interesting, right? Because we could do that on all the other ones. The thing that's interesting is where we have this guy. Okay, and so there's a plus charge on here, right? So what's cool and interesting is if we actually take this bond, kick it down here, right? And then we can move this bond onto the nitrogen. And yeah, then this should move on to here. Yeah, right. Yeah, that looks right, I think. Yeah. Okay. Right. And so this stabilizes the conjugate base. Okay. All right, and then in B, which of these is the least acidic phenol? Yeah, and so, okay, so most people wound up saying it was A. Okay. And so, again, majority wins here, right? So yeah, so it was A. That is the least acidic, right? And so in a little bit, this is kind of like a ranking question in disguise, which, okay, cool, right? This is the least acidic, right? And does anybody want to tell me why it's not B? Nobody voted for C, which is good because that was the previous one, right? Anybody want to tell me why it's not B?
Is the inductive effect involved?
Exactly. Yeah, it is. Yeah, that is exactly why. So this structure here, so this doesn't have good resonance. Okay. But it does have the inductive effect. Okay. So we'll take what we can get and we'll have this inductive effect, which does wind up making the phenol more acidic. Okay. Not by much, but well, it's something. Right. You could draw out the structure for this and try doing the resonance. What you should find is that there's no way for the electrons from this oxygen to make it onto that NO2. So yeah. Also, do remember that NO2 is one of the strongly electron withdrawing groups. So when it comes to the inductive effect, NO2 is really good, right? Oftentimes we just think about like the halides being really electron withdrawing, like bromine or chlorine, but well, or really fluorine is kind of a common one, right? But NO2 is also really strongly electron withdrawing, as are carbonyls. Okay. Good, let's look at C. Okay, so the compound that contains an axial bromide, right? Okay, and most people wound up saying B. So let's look at this, right? Okay, so for question C, right? Let me move back and forth a little bit here. Okay, so why don't we draw the first structure, right? And you'll notice that the first structure is this sort of transdecalin, right? Which is these two guys are on opposite sides, right? So if we just draw out one of these rings, right? We'll draw out this ring, right? And then we have the methyl pointing up here, and we have the hydrogen pointing down, which is good, and that means that we could just stick another ring right on, like that. Okay. So this is like what the structure of like transdecalin kind of looks like. Here. Oh, okay. So somebody actually asked about B, so why don't we ask about why don't we talk about that one a little bit more? So why doesn't it have a good resonance? That the electrons are shared around the carbon ring equally, so there shouldn't be any difference between the two. Yeah, so the reason that is like, so the electrons are shared equally around the ring, but like the positioning of each different group kind of affects the different other areas differently, right? This is a point that like will get driven really hard home next semester, which like, look at that, we're even at the end of this semester, and I'm still saying that. But like there is some value to drawing the structure out like this, because it gives us information about how each position affects the adjacent ones. So for example, if we wrote out, you know, what's a good electron withdrawing group, I don't know, let's just pick well, let's just put chlorine here for you know, good reason. No, let me not use chlorine because it's a withdrawing group, but it kind of does funny stuff on rings. So I don't know. Let's put a carbonyl, right? That's a good one. Okay. And so let's kick these electrons up. Let's kick these up, right? And so what we find drawing the resonance structure this way is that it'll look like this, and there will be a plus charge over here, right? And you can move the electrons around, and you'll find there's a plus charge here too, and keep moving them down, and you'll find that there's a plus charge over here too. Okay. If we drew it this way, right? If we drew it the other way, so let me rotate all these bonds, right? What you wind up seeing is electrons move over here, and you'll get the plus charge here, right? Move these electrons down, plus charge. Move these, also a plus, okay? So these two structures, whichever way we drew the double bonds at the start, we wind up getting that the electron localization, like the places that positive and negative charges tend to be, wind up in the same spots. Okay. So the idea is that, and this is like, you might say like, well, this isn't even real at all because like these three bonds like don't exist, right? Like it's really just like a big circle, and you could just imagine sloshing your electrons around in a circle, right? In reality, this is actually what we see. like this is like you can run experiments and look for the electron density, and this is really what does happen. So while like yes, it's true that these like drawing it out in this like 3 bonds way is not really real. Like the electrons do localize in this way, so it's a like a reasonable representation of what actually happens. Okay. So like, yeah, while it is like really this circle, but like in kind of in practice about how the electrons move around, they do follow this sort of pattern, right? So when drawing these resonance structures in general, this is the way to go. Which is to say that the positioning between this alcohol and this NO2, they're positioned in a way relative to each other that they can't interact by resonance. Okay. All right, cool. All right, so here's back to C. Here's this one structure, right? There's a methyl, there's a tert-butyl here, right? Okay, well, good, we got lucky. We drew it in a way that the tert-butyl is equatorial, which is what we need it to be, right? And then there's a bromine, which is pointing up on this carbon. So it's pointing up like that. Okay, that's equatorial, so this is not it. Okay, all right, well, we got to do some more work now, right? So now it's just going to be the difference between these two guys, right? And that means we'll start by drawing our ring on the left, for example. I mean, well, I guess we could draw either one, but we'll draw it in a way so that we force this tert-butyl to be equatorial, right? Put a hydrogen down just for good measure. Then we put the methyl here, and then the hydrogen goes up here, right? Oh, and now this is like the worst part ever, right? Because we have to draw on the rest of the ring. So this part of the ring is equatorial. This part is axial. Okay, we're 4/6 of the way there. We just got to fill in the rest, right? Okay, and so let's see. All right, if we're working with a ring, if we're looking at this ring, this is going to be well, it's worth saying this is the point at which breaking out a modeling kit would be pretty helpful, right? Like this is like one of those situations where that does really make the difference. Yeah, if we wanted to draw in the rest of the structure, it would likely, I don't know. Well, that is super ugly, right? That also might be missing. That is missing a carbon. So it should look like this, except, you know, actually better and more nicely drawn. Yeah, so well, okay. This carbon is going down. Damn, I've been able to do this before, but this is like rough. Okay. Okay. Well, that's not a very good way of drawing it. Yeah, for some reason I'm blanking on a good way to draw this as a Cherenkov formation, right? Because drawing it on the page is like a real pain. Yeah, so okay, most of you did say it was B, which is good. The key that I have says that it should be C, right? No, you guys don't like that. Okay. Yeah, okay. So well, yeah. If you do have a modeling kit, this is totally the sort of thing to try out and test, right? because maybe it will be B. Okay. Well, Danielle has one, so Danielle's on it. Yeah. Most of you said B, and looks like a good few of you have modeling kits. So I'm kind of inclined to believe you on this one. Yeah, it could totally be wrong. What I haven't.
Can I interject quickly?
Yeah, of course.
I feel like depending on the position that you hold it in, like right now, I guess I'm reversed, but so this is like the first ring that you drew and this is the second one. So right now the bromine is axial, but if you flip it, then it would be equatorial. I don't know if you could see that. So I feel like, I don't know. That's why I can see that you might say it's both, especially since it is one removed from the shared bond. Like, I don't know. That's what I see.
Okay. Yeah. Yeah, I guess I see what you're saying. Maybe it would be more responsible of us to draw the ring on the left, right? And then kind of determine how that fixes the ring on the right. Right, if we draw it like this, okay. Right, and so this hydrogen now points up and this methyl points up, right? Oh, look at that, I did it. Okay, I just had to redraw the structure, but now we got it. Yeah, and so, okay, let's draw this compound B first, right? So 2 over from the hydrogen, we have a bromine and it's pointing down. So, whoops, not an arrow, but a BR here, right? And so there's going to be a hydrogen pointing down here, and then this tert butyl is pointing up. So that means this tert butyl is going to be axial on this one, right? So this is B. And so if we, well, but this structure is no good, right? Because this guy is axial. Okay. Yeah, and if we draw the structure this way, right? Like that, right? This, okay, then this tert butyl is still axial, right? But that means we ring flip it. Oh, whoops, this bromine should be up. Ring flip. So now we get an axial bromine. Okay. So doing it out this way, at least on the page, I wound up getting it C. Okay. Let me just get rid of this disaster that I was trying to do earlier, right? Yeah, but if you have this modeling kit, you might be able to work through it a bit better than doing it this way, because this is kind of shady. Okay. Yeah. Okay. Yeah. So based on this, it looks like it should be C, like the key winds up saying. Although, work through and play with this one. Okay. If people really strongly disagree with me, then, well, there's a little bit of room for debate, but it does look like it'll be C in this one. Okay. Hopefully there's not wild outlash and people don't go crazy.
This might be obvious, but like, how do you know that the tert butyl is axial? Because like it's the same, like it's like also like up on like the same ring as like in A, which was equatorial. So like is it from like drawing it that you know that it's axial?
Yeah, it's in this case I drew these two. I drew this ring and I drew these rings differently. well, I should say I drew. So this ring and these rings are drawn differently in these two cases. Like the way that I've typically gone about these problems is to just draw the ring, fill in the substituents, and then ring flip as needed to get what you need, right? So in this first case, we drew the ring. Conveniently, the tert-butyl was equatorial, and so we just kept going from there, right? Okay. In the other case, we drew this ring on the right first because that's kind of the one that we're interested in, and then I filled in the rest, right? And it wound up being that the tert-butyl was axial, right? Unfortunate, but well, we can do a ring flip, right? And we know how this bromine will change if you do a ring flip. On top of that, fortunately, this is transdecaline, right? Or an analog of it. Transdecaline is this is cisdecaline, right? Cisdecaline is actually able to do a ring flip, so that's good, right? This other one here, this transdecaline can't. So yeah. Okay. So it winds up to me looking like the answer should be C. Okay. Spend some time, work through that one. Maybe we can come back to it. Okay. All right, and then for D, the answers were really split between B and C. Okay. Very slight preference towards B, but well, not by much, right? So why don't we actually take a look at it, right? So resonance structure of A, okay, which, well, let me just copy it from my other screen. Okay, so compound A looks like this, and then there's a nitrogen, right? And let me just fill in the electrons while we're at it because, well, yeah, right? And the question is not a valid resonance structure, so why don't we just go through and actually draw them, right? Okay, move the electrons up. Let me use a different color, right? So move these electrons up. Here we go. There's no double bond there, right? An O minus. Okay, and there's a plus down here. Okay, move this bond over. Let me do it in red again. Oops. Okay, there we go. So now we move the double bond down here, right? Notice, by the way, that this is an enol now. I mean, there's a plus charge next to it, but still, always good to keep that in mind, right? And there's that those electrons. Okay. So let's move these electrons down, right? So we can make a double bond with this nitrogen. There's a plus charge here. Okay, cool. This final structure here, this is A, right? Well, this is the first of the three resonance structures, potential ones that they give you. Okay, so okay, that one's definitely valid. I now also see why the answers were split between B and C, because they look like they're both wrong. Yeah, you can't have an oxygen with just one bond be a positive charge. I think the last of the three structures were supposed to be a minus on oxygen and a plus on the carbon, right? So for reference, this was the so for reference, I think it was supposed to be like this and like this. Okay. But I see why you guys put that, right? And I have the feeling that most people got the idea that B wasn't right either. Okay. Yeah, so this is wrong, but this is also wrong in the worksheet. Okay. Sorry, did not proofread.
Wait, Adam, I have a question about like why the one that like is also wrong. I thought the two electrons from like or like the electrons in the carbonyl double bond could just like move down.
Oh, can they? Yeah, maybe it's not wrong. Maybe I jumped to.
Like can they
I
move?
don't wrong because like on like question or on quiz 1 or whatever, when this was a very similar question on it, like one of the valid resonance structures looked like it was like the equivalent of that basically.
So you said you don't think they can? Or they can?
No, I think Emily's right. Like it should be able to just move down and then the carbon's negative.
Yeah, I guess it just moves down to here and. Oh. Yeah, I guess you guys are right. Yeah. Thanks for pointing that out. That's ugly. Right? But I guess there's yeah, you guys are right. Never mind. I take that back. This is a valid resonance structure. It's not one that we would usually write because this oxygen is so unhappy, but yeah, you could do it. It's because this oxygen only has 6 electrons, right? Or yeah, which is really unusual. Or 5, well, yeah, 5 formal charged electrons, right? Because this only contributes 1. Yeah. Okay, never mind. Let me go fix that. Okay, so B was in fact the sole right answer. Yeah. Yeah, you said this was on like the first quiz or something. Something's really similar.
Something really similar, yeah.
Okay. That's kind of ugly. Yeah, okay. So it'll be B in this case, right? Because this one we definitely can't get because we can't make a double bond with this methyl group, right? Like that would involve removing a hydrogen. That's not resonance. Okay. Good. Yeah, actually, someone pointed it out in the chat to me, which is a good idea too, that if you, for question C, another way that you might be able to do this is just to like kind of walk your way along the carbons and just do that, right? So if this is equatorial, right, then this will be axial, this will be equatorial, axial, equatorial. I don't know if that works. No, I don't think it does because there's some weird stuff that happens when you go here, right? It's so this guy is this is axial with respect to this ring, but that means it's equatorial with respect to this ring, and so you have to restart, and so you go equatorial, axial. Okay, that's kind of complicated. Okay, but we don't have to get way too into that. Okay, let me put some more problems on here. Again, we have a whole ton of problems to go through, so I need to talk about. Okay. Here we go. We will just, well, no, I'll put both of them down, but let's paste. Oh, look at that. It's right in place. That's really convenient. Okay. So the second of these involves Newman projections, which we haven't focused on, right? I will draw out the structures because you don't need to know Newman projection, or sorry, these Fisher projections, you don't need to know these. Newman projections, you totally have to know them. Okay. So why don't I? Oh no, I don't want to relaunch the same poll. Here we go. Let's. Okay, so there's a new poll now. So why don't you take like 2 minutes, work on these. Let me draw out the structures for F. Okay, let's do it. Question E. So here in this case, most people went with C, although a few also went with A. Okay. So the question is not a conformational isomer of B. So it's just with conformational isomers, we're just rotating the molecule, right? So okay. Well, this one, they rotated the molecule around the whole thing, right? So they took the whole molecule, right? And they did one of these rotations, right? Like if this is the whole molecule. Okay. They rotated the whole thing around this way. So that's already, we're dealing with that, right? So if we do rotate the whole thing around, what we'll wind up seeing is up in front, this ethyl group stays, right? Stays up in where it is, right? But everything around, whoops, swaps places. Okay, and same thing with the front, which winds up going to the back. This methyl group stays on the bottom, right? But the alcohol flips over to the left, and the hydrogen flips over to the right. Okay, and so now we do our rotating, right? So up in the front, we wind up cycling these three guys up in the front. Okay, and that gets us what this guy has up in the front here too. Okay, and then in the back, we wind up rotating everything the other way. Okay, so in the back, we wind up taking this, moving it in, moving all three of these this way. Okay, and you wind up getting the same thing that's in the back of A. Okay, so we rotate the back that way. Okay, and that gets us A. Okay, so that works, right? Over here, well, let's take the same thing. Ethyl, again, they rotated the whole molecule around, right? Just to give us some extra work, right? Okay, so here we go, OH, H, and a methyl, right? And hopefully if you're doing this on the exam, you might do this a little bit less sloppy and might do this more carefully, right? But well, we take this whole thing gets rotated, right? So that's kind of a pain. Let's see if I can, this might be a bit too advanced for me, but what if I take this thing? I think I can rotate it. Oh my God. All right. Look at that. Okay. Did it. I need to be a little bit more technical. Okay, cool. Yeah, so now look at that. The front is already exactly how we want it, right? Ethyl, alcohol, hydrogen down at the bottom, right? And now we just take the bottom, the backside here, and we rotate with blue, right? So we want to move the methyl. Oh no, it's not going to let me write. Let's do new layer. Oh my God. Oh, that would be why. Okay. It's painful. Okay, all right. Okay, now I can write. Sorry. This is the worst technical day on the planet. Now we take the back and we just rotate in blue here. Rotate the back. Right? And this whole thing, this gives us B. Okay. And now if you really want, okay, we did process of elimination, so it's going to have to be C. What you can show here, what you really show in the end is that this structure here in C, like the entire order of some of these substituents is just flipped. Okay. So if we draw what we had in the front here again, so we draw ethyl, and then the hydrogen goes here, and then the oxygen OH goes here, right? That's fine. We like can't wind up rotating what's in the back. Okay, it's fine. So if we place that oxygen down, right, what we find is that this place should be a methyl and this place should be a hydrogen, right? Same as back here. But I mean, that's obviously not the case in this example, right? This methyl here is a hydrogen here, another way around. So they're just different molecules. They're not the same configuration. Okay, so for F, right, like a good amount of you, like 2/3 or so, wound up saying B, right? The rest of you said A. So again, this is just another situation where we sort of have to like move the molecule around in space, and this could be like a situation to just break out the modeling kits and go to town on those, right? In this case, so for A, what I think we want to do is rotate the whole molecule around like this way to do A. And so let me do it in a color for A, right? So we do that, and we wind up with a bromine down here, right? Well, both bromines are down here. Okay, and so let's see, these guys will like wind up flipping. So the methyl will be up front here, right? This is the hydrogen, and then, oh, it winds up being the same thing, right? Doesn't it? Yeah. All right, well, we didn't have to do that because this molecule you can just flip around and rotate anyway, I guess. In that case, that just means we wind up having to rotate this stuff, right? So let's cycle these three, right? And then on this side, oh, yeah, we didn't have to do all that work, right? So just to say, don't even bother doing this, right? Like, skip flipping the molecule that way. You could just rotate each side of it individually, and you wind up getting the same thing as what's up here. Okay. All right. Well, in terms of B, what we'll notice is, let's say we take the starting structure, right? H, there's a methyl here. There's a bromine, right? Let's rotate this side to get it in place, right? Because we could do that. This side will work. And you'll notice that there's no way to rotate this side of the molecule, right? Here, we just have to swap out this hydrogen and this methyl. So that means it has to be B. Okay. For C, you can go through the work too and show that it has to be. You can show that you can get back to the original molecule from here, right? In particular, rotate this side this way. Okay, and this side, let's see. Here is different. Maybe you have to do some extra molecule flipping around to get here. Or this might be an enantiomer, which is not a diastereomer. That might be the case, yeah. But we found this B, and we got that as a good answer, so that works. Okay.
I think C is the enantiomer, because I did it by finding the stereocenter, like R versus S.
That's another way to do it. Okay, good point. So this is actually, this is an enantiomer. Okay. Cool. So let's keep going, right? Okay, those were some multiple choice problems. The rest, or a couple more from now, are actual describing and kind of concept. concept questions, right? So 2A, which is on the worksheet, and I'm not going to copy and paste it because I can just write it easily. And you have the worksheet. It's on the workshop canvas. Again, you send me your email or shoot me an email if you're not on there, right? So the difference between basicity and nucleophilicity. Okay. The question is, what is the difference between those, right? And I imagine that one of you could probably explain it better than I can at this point. So anybody want to try?
So from like what I have written down, I said that basicity is a thermodynamic equilibrium for deep protonating a proton, and nucleophilicity is the kinetic rate of attacking the electrophile.
Yeah, I could not have put it better myself. So basicity is, it's all about equilibrium, okay? Right? So that would be like a base attacking something and pulling off a proton. Right? Okay. That's what basicity is all about. And then, yeah, and then nucleophilicity is about kinetics, right? It's about the rate at which something attacks, right? So okay, so if you have like a nucleophile, right, that might come in and knock something off, right? It's just a one directional arrow. Okay, that's what nucleophilicity is all about. Okay. So the next question then is, at least on here, is to, well, yeah, so anyway, okay. This is the difference between basicity and nucleophilicity, right? Remember that they kind of compete, or at least they certainly can. Nucleophilicity we can change by making like something really bulkier, for example. We could do that. I guess we could do that with basicity too, right? If you have something that's really bulky, then it'll wind up being less basic because it's less likely to do a reaction. It's less likely to attack onto something, right? But these two will compete all the time. Okay. Anyway, so the next question is to sort of describe what we mean when we say polarizability. Okay. Like, what does it mean to say that an atom is more or less polarizable?
I guess it means that you can get like a dipole in it, kind of, that you can like have all the positive charge on one side and negative on the other, and it's not like physically like that necessarily.
Yeah, exactly, right. And in practice, what this really like means for us and why it's good is because it means that you can kind of get like partial bonding, right? Like what you could do, for example, is if you have iodine, right, and it's got this big ball and it's like a bunch of pluses and minuses, you can kind of separate that out, right? So like the minuses are on one side and the pluses are on one side, on the other side, right? And all these minuses are going to be really good, for example, for like this situation, right? Because this carbon is kind of positive and this halogen or leaving group is kind of negative, right? So these guys being here makes it a lot easier to make a partial bond, okay? So you can get this sort of situation, right? Where this is like a transition state and we get this, TS, okay? Okay, and yeah, and polarizability will make things better nucleophiles. Okay, precisely for this reason, because they make it easier to partially to do like this sort of partial bonding. Okay. Okay. Good. And well, this might be kind of easy given what I just wrote, but the next thing is to give an example of a stereoselective reaction. Okay. And does anybody just want to tell me what the stereoselective reaction we learned is? Like the biggest one?
SN2 because of flip stereochemistry.
Exactly. Yeah. So SN2, pick your favorite. It could be, you know, totally anything, right? Let's just do something like this, O-tosyl, right? And then I don't know, whatever like the whatever a good leaving group is. I don't know. This guy is or a good nucleophile, right? This is a fantastic nucleophile. That works, right? I mean, this is a kind of also basic nucleophile, so you'll get some E2 going on, and that's kind of, you know, that kind of gets in the way. But pick your favorite nucleophile, and this would work, right? This is stereoselective, which is good. Okay. So now, this is all part of the same question. Now this goes on to ask. We're back to the same situation. Ask to rank the acidities of these compounds, right? And there's like no escaping ranking acidity for these. So let's move this down here. And let me put up the poll, and there we go. Okay. So some of this just involves knowing the pKa's, but some parts of it also involve just, well, I guess it's largely just about knowing the pKa's, but that's good. You should know that anyway. Let me give you a minute to do it. Okay. Everybody ready? Get your votes in if you haven't. Okay. Okay. Seems like most people wound up saying that D is the most acidic, but a few people said that E was also pretty acidic. So this structure here is just this guy, this SO3H here. This sulfate group is really, really stable under resonance because of resonance, right? It was really acidic. The pKa of it is like, I don't think it's mentioned very often, but the pKa of it is really low. So I think it's like -2 or something like that. Meaning it's like super acidic. Like it's basically never protonated. Okay. What's the pKa of this guy here? Which most people said is second most acidic?
I think like 5.
5? Oh, okay.
For
I
carboxylic.
remembered it being lower. I thought it was 2-ish, but I might be, or like, oh no, that's for like amino acids or something, which come up later. But
Google says 5 also.
okay, all right, then let's just go with 5. It doesn't make a huge difference, right? Because I mean, these are all reasonably separated apart. Okay, what about phenol? Here, this first one.
Isn't it 7?
7.
10?
7 to 10. Yeah, it's somewhere in that range. The number that I always keep in mind is 10, but they could be more or less acidic depending on what you stick on there. So, you know, that works, right? So this will be 3, and then 4 and 5, we might guess. So this alcohol, what's the pKa?
Like 16?
Yeah, it's like 16, and this guy over here is like 45 or something ridiculously high, to the point that like this is never going to be acidic. You don't need to worry about it. Okay. Good. That's what most people said. Yeah. This guy C is just never going to release protons. So. All right. Let's get some more problems on then. Let me save this document. And let's make a new one and put some more problems on. Okay. Which are going to be more like multiple choice. Select the answers, because, well, there's kind of a theme here. Okay. Move these up, and then let me get the other problems too, and we'll move. I don't know why this box is being weird. That's okay. Here we go. Let me put these up, and then I'll leave you guys a few minutes to figure these out. Okay. Is the polling open? No. There we go. Okay. So again, here's five problems. This last one has Fisher diagrams. I'll fill in with what it should be. Okay. Okay, 13 of you voted. So we'll take it. So let's 14. Oh man. All right, nice. Okay. 15. Okay, let's do some of these then. Okay. The first one was circle the most basic amine, right? And an overwhelming majority of people said it would be C. Okay. And does anybody want to provide a really quick explanation without going into tons of detail? Anything?
The
No,
carbon.
inductive.
Go ahead, Danielle.
Oh, I was saying like there's no like inductive effect thing, so it's essentially makes it a bad acid, right? And like,
Okay.
where's that?
Yeah. Well, that would be in terms of the conjugate acid, right? So that's a good way of thinking about it, right? So in this case, both of these conjugate acids for these guys, right? So let's say we draw out either of these. In other words, both of these do have an inductive effect going on because this carbonyl is a withdrawing group, right? So that means that both of these will be more acidic, right? And so that means that these guys will be less basic. Excellent. Yeah. I mean, good. Yeah, you could also think about it as being just purely a withdrawing thing, right? I mean, amines are trying to give or bases are trying to give their electrons away, right? But it doesn't help if you have this carbonyl that's there that's saying, no, I want your electrons instead, right? So withdrawing groups will help acids, but they harm bases, is kind of the point. Okay. But translating that into conjugate acids is like the formal, probably a good way of doing it. Yeah. Okay. That's good. Most of you wound up saying C, which is good and helpful. Okay. The second question, B. Most people said C, although one or two said it might be B. Okay. So, okay, if we have a Grignard, right, and it's going to be like MgBr, let me just use some, I don't know, R, right, whatever carbon group, pick your favorite. So if it attacks onto B, what'll happen is, well, we'll get this ring, which I'm just going to draw like that because I'm too lazy, right? This O minus, right? And here's a hydrogen and whatever we just attached, right? And then we do aqueous workup, right? And there's our ring. Now we just have an alcohol, but there's a hydrogen there and our R group. So this is just a secondary alcohol. The reason especially being is that you just can't remove a hydrogen. Like hydrogen is like the worst leaving group on the planet, so it's not going to happen, right? Whereas here, repeat the process, right? There, O minus, right? Here's a methyl, and then here's our R group, right? Okay, and then you can protonate it, and then you wind up getting exactly a tertiary alcohol. Okay, so it'll look more like C. This third one. Okay.
Wait, I
All right.
have a question on that
Yep.
really quick. So I was looking at, I think, some review sheet yesterday, and when you have a Grignard, just with an alcohol in general, it deprotonates the alcohol. Like say it was just attached like over to the other side, it would deprotonate the alcohol, and then like whatever was attached to the Grignard would kind of just be in solution. Like what is, I guess, going on there?
Yeah. So
And
that's
does
just,
that happen here, I guess.
yeah, I think so. I think what you're talking about is just like a standard acid-base reaction, right? So if we just have like an MgBr, right, we can kind of think of this as being like MgBr plus, right? And then you can have I don't know, whatever other structure you want, right? Let's just pick like, screw it, let's really go wild and go with like this guy, right? There's a minus here. This will just do your like normal acid base, right? This is like a really basic compound, so it's just gonna come in, take that hydrogen off, and this will give us down here, well, it'll give us this O minus, and then it needs a counter ion, so let's just give it this MgBr plus, right? And then we just wind up with this guy.
And that doesn't happen here because it's a carboxylic acid, like it just attacks. It doesn't split it, I guess.
So it will deprotonate this first.
Okay.
Yeah. Which is what makes one of the big reasons that makes carboxylic acid so bad at reacting with Grignards and organolithiums and cuprates and all that. Because you remove this hydrogen, so you already have a whole bunch of negative charge here, more than you're supposed to, and then you're asking to put on more negative charge by attacking it with a Grignard, right? Like that's just not going to work.
Okay, thank you.
Yep. Okay, and so let's see, next one was a little bit more split, but it was largely towards A, or this first structure here. Okay, so there's this chlorine over here, right? And so it says this ratio is 5.5 to 4.5 to 1. Okay, and so the idea is to count out how many of each type of carbon that you have, each type of hydrogen that you have, and from there multiply it by these ratios, and then you get a number and you can compare, right? So in this case, this is tertiary hydrogen, this is tertiary hydrogen here, right? There's 2 of them, whereas there's 3 of these hydrogens, so there's 12. Let me do this with colors, right? So there's 3 hydrogens here, there's 3 up here, 3 over here, right? So 4 times, yeah. So there's 4 hydrogens at each one, right? Times 3 total. So there's 3 hydrogens that each one, 4 total of these places, right? And then they're each primary, so it's times 1, so we get 12, right?
Wait, Adam, aren't there more hydrogens on the methyl groups on top?
Yeah, so there are, but they're different. Because they're just sticking off like this, like just drawing out this structure. You are totally right, and I left them off for this reason, is because just drawing this structure, like these 4 hydrogens they're different from these up here. Like if we chlorinate these hydrogens in black, and if we chlorinate these hydrogens in blue, they'll be different structures.
Wait, can you explain how they're different? Are they both primary or?
Yeah. So I should be more clear. They are both primary, but like they're in different spots. So.
So like they produce different like isomers as products, right?
Exactly.
Okay.
Yeah. Yeah, exactly. So chlorinating at these red carbons as opposed to these blue ones will produce different isomers, just like you said. So over here we have 3 and 3, right? And so there's 2 carbons times 3 hydrogens each times 1 for the reactivity, so that's 6. Okay, right? And now over here with these black hydrogens, right? Well, there's only 2 of them. Okay, 2 total hydrogens, but their reactivity is 5.5, right? Which should give 11. I'm doing my math right. Yeah. And did I do my math right? I hope so. Yeah, I'm pretty sure it should be A. Maybe I did something wrong along the way. Yeah, let me double check, but I think it's A.
How do we know that we're supposed to be like counting the number of hydrogens that are a certain thing? I don't feel like we did this before.
Oh, I guess it's because like it doesn't matter which hydrogen you pull from, and so the more hydrogens that are there, the more likely you are to pull those, right? Just out of the number of them that exist. Like, yeah, it's sort of the idea that, like, let's say, just as a really simplified example, let's say that you were just working with this structure, right? So is these guys, right? And then up here and here, right? We have let's say these are different, right? Just because they're distinct. Okay.
So it's like if you did any of the black ones, it would effectively give you the same molecule as if you did, and then like separately if you did any of the red ones.
Yeah, exactly. And well, what that means is that there's just more of these black hydrogens, so you're just more likely to pull one of those, right? Let's say you have a totally equal chance of pulling any of them, right? You'll wind up with 6 times this guy, and then 4 times this structure.
And that's because chlorine's not as selective, right? Like if it was bromine, you would end up with more red.
Yeah, exactly, right? This is just assuming. So this is assuming it's equally selective. Or assuming totally unselective, I guess. Okay. If they give us selectivity, like this problem did, then we've actually got to pick. Okay. So they give us this selectivity here, right? And so, or, well, yeah, now we got to multiply, right? We can't just make that same assumption. We can't just count the number of hydrogens there are and pick that, whatever's the best, right? So we multiply by the reactivity, the relative reactivity, right? So these tertiary hydrogens are, there's 2 of them, so times 5.5, we get 11, right? These red ones are 12, blue ones are 6, okay? So it actually turns out that that this structure over here is the right one. This is the most likely. Okay.
Wait, so we want the lowest number, not the highest? Isn't that only 6?
So in this case, you want, yeah, so you want the highest relative reactivity, right? Whichever one will tend to react the most. It's not this. Yeah.
I think it looks deceiving because he drew the blue 3s on that one, but I think that he's referring to the one that he did on the left. That,
Sorry.
but yeah, it's the same. Yeah.
Yeah. Good point. Yeah. Good. Okay. Let's see what's next. Okay. Oh, things were pretty split on D. So the compound that will most readily participate in E2, right? And now, well, we're doing this again, right? Similar situation. We're working with this decalin, this ring, and we got to be able to write out what's going on. In this case, 2 of these are this transdecalin, which is much easier for us to draw and work with, right? So throwing a ring down on the page and then filling it with my bromine, right? Here's a methyl, here's a hydrogen. Let's add in the rest of the ring. Oh, there we go. Yeah, there we go. There's the rest of it, right? Okay, this last one is looking really convenient for a ring flip, for an E2, because we're already anti-periplanar, right? And remember that transdecaline this can't ring flip. Okay, so we're stuck in this conformation. So this is pretty nice because we're kind of already just stuck here. We know that we're going to be in this position. We can't move. Okay, so like a slight majority of you said, this last one would be the right one. Okay. In this one right before it, well, we can draw out the structure. Let's plop down a ring, right? And then there's this bromine that's pointing up here, which is just this bromine is equatorial, so it's not going to be able to do E2. Okay. And then you could do the work on this first compound if you want. You can go through that same trouble and pain that we went through with like the first problem to do it. But there's fortunately no need here because we already know that this last compound is locked in a good position for E2. So no point in going through all that work. Okay, last one. Which is a diastereomer. Okay. Let me also move what I had drawn down here. Right. Oh. Select. And move it. Get it just out of the way. Okay, good. All right. So last thing is, which is a diastereomer. Okay. And this is again another just similar situation, right? You might want to start by just drawing out what this structure looks like. Okay. So let me put the front up on this side and the back on that side, right? So CH3 goes over here. There's a hydrogen that goes in the back. And this amine NH2 goes up front. Okay. Methyl down, right? We've rotated it. So we gotta go through all that mental work, right? And there we go. Okay. Consider building a model, or generally take your time in this case because it's an easy place to, you know, put the wrong atom in the wrong bond and that'll kill you. So yeah. And then from here, let's see. So majority wound up saying it was C. Okay. And so the easy way we might just be able to see that is that there's no way of rotating this molecule. So first let's rotate the whole thing this way. So we get the amine on the right side. Okay. And the point is that there's no way to rotate the bonds here so that we get the same thing that we started out with. Okay. So this hydrogen now moves up front. This OH goes back here. Methyl down here. Okay. And well, yeah, if we go through, we do the work. Okay, we can rotate this side and this doesn't even come out right. Okay. So if we want to get back to the original structure, we have to flip these. And so that means it's a diastereomer. Okay. and you can go through, I mean, and you can go through 1 and 2 and show that they're either enantiomers or that they're just the same molecule but rotated in some special way. And that would get you here. Okay. So it is 1:17, so we've gone a little over time, but that's okay. We just do that normally anyway. Okay. There are more problems on the worksheet, and I much recommend that you go through them and do them. They're really good practice, hopefully, we think, for what will come in the exam soon. Okay. People feeling okay? I hope so. Okay. There's a lot of practice. I've uploaded things on Canvas, and I'll put the review guide and the recording and all that on Canvas pretty soon. Okay. I believe in you. You will do well and amazing. And good luck, I guess. Okay.
Thank you.
Thank you.
Yeah. Hope you I hope it goes well. Okay. Okay, good. Let me save this stuff. I'll upload it, and that's all we got, right? Okay. Okay, in that case, it's been
Thank you.
fantastic leading workshops, right? I always love sharing in the chaos of Orgo. Fortunately, I don't have to be the one taking it anymore, right? But it's okay. In a few days, you won't be either. All right?
Yeah, it's
Good.
been very helpful.
Sound good?
Thanks for teaching
Yep.
us.
Thanks so much, Adam.
Yeah.
Thank you.
I'm glad I can help you guys. Okay, let me close the meeting. Bye.